Roller coasters. Is there anything they can't do? Before going into the details of the massive acceleration of a roller coaster, you need to understand that a roller coaster uses a combination of gravity and inertia along with g-forces and centripetal acceleration. Initial potential plus initial kinetic energy equals final potential and final kinetic energy of a roller coaster at any point in the ride. Because of this, after the initial lift at the beginning of the ride, most roller coasters use transformation of potential and kinetic energy through lifts and declines to power itself to the end of the ride, bearing extreme friction, wind, or other minor external forces. In order to find the potential energy of a coaster at one drop, you would need to find the mass of the coaster and the height of which it is dropping. Let's say the mass of the coaster is 300 kilograms, and referring to this picture, the height is 25 meters. Then multiply the height and mass by gravity, which is 9.81 meters per second squared, and the answer will come out to be 73.6 kilograms meters per second. In addition, potential energy for the coaster is highest when the coaster is at its highest point over the course of the ride. Centripetal acceleration points towards the center of the circular path of the coaster, but is felt by passengers as a force pushing them to the outer edge of the path. Although often referred to as a centripetal force, there is no actual force pushing the passengers or pulling them from the path of the track. The force is actually your body resisting the train's change in direction. In this equation, AR is centripetal acceleration, V is velocity in meters per second, and R is the radius of the circle of the track in meters. The faster the cart goes around the curve, the more force you feel. Coasters usually bank high-speed turns to make the passengers feel the force straight down into their seat rather than off the outer side. Banking a curve also allows for greater speeds and quicker turns, which leads to more force felt. To find the centripetal acceleration, simply plug in the velocity squared and the radius of the turn into this equation and divide. Roller coasters use potential and kinetic energy to speed up and slow down with lifts and declines. Energy transfers from potential to kinetic while going down a decline, and from kinetic to potential when going up a lift. In the ideal roller coaster, all energy would be conserved, but in real life, energy is lost to friction. In this equation, E is total mechanical energy, K is kinetic, and U is potential energy. We can derive this equation since energy can't be created or destroyed.